Hello, this is a series called KillerRabbit Codes where I simply just program, and today we'll be talking about something I call effectful language or an introduction to algebraic effect handlers. And this is just an overview of the project I want to work on. So, what's the motivation for this? Well, first we need to know about what are algebraic effects and handlers. In most languages, side effects are implicit and can happen anywhere. Side effects can be things from mutating a global variable to accessing something over the network or throwing an exception. In these languages, the caller has no control over what the function they are calling does. Algebraic effects make these side effects explicit and interceptable. A handler provides the implementation for the side effect is like a try-catch but much more powerful, as rather than just unwinding, it also supports resuming. What are algebraic effects useful for? Algebraic effects generalize side effects and allow us to express effectful computations. They also compose cleanly compared to things like monads. For example, we can build the machinery for an async await setup or implement try-catch within the language's standard libraries. Since they're more composable, it also makes testing easier as you can simply change the underlying handler for testing, mocking, logging, or retrieving, or retrying. So effects are great. How can I use them today? A great language that has algebraic effect handlers is called Koka. It isn't quite usable for production systems today, but most of the main features of the language are there today. Here's an example of a Koka program taken from the official documentation. So what I will be building. I'll be building a virtual machine that natively supports algebraic effect handlers. Most of the work will be done in this regard. There may be a programming language made to be more to thoroughly test things, but that isn't the focus of this project. The focus of the project is to build a runtime. And you might be wondering, how do you build a virtual machine? There are many guides on how to build your own programming language, such as crafting interpreters. There isn't very much on how to do it with effect handlers, so I'm mostly on my own with just research papers on how to do it. For this project, we'll use what's called a stack machine. Operands are pushed and popped onto a stack, and operators manipulate the stack. The benefits of this model include it's very easy to implement. I'll be using Rust to implement the VM, as is what I'm most comfortable with. And it provides enough low-level control that will be needed in such a project. And so what are the first steps? So today's first episode, we will be building the higher-level data structures that allow us to easily test the virtual machine's interpreter. We will provide 3 different layers of a module file. A high-level one, which will write all of our test code in. A partial serialized form, which we could use as a more sane checking, and then a completely binary format. Binary format will basically convert everything into, so then we can read it in our interpreter. And we'll test that serialization between these forms is clean. On later episodes, we'll actually build out most of the interpreter. The remaining episodes will be building out the effect system as well as additional features. What this won't be. This will not be a tutorial on how to build a programming language or how to build a stack-based virtual machine. It'll mostly be documentation of me working on a project in a freeform style. I do intend this to be somewhat educational since I want to share the fun of algebraic effects with the greater computer science community. I think there is a real potential for this feature to become mainstream in 10 years or so. Thanks for listening to this portion. The descriptive portion of this episode is now over, and so now we'll do the programming portion. Right here I have a Emacs window open, and what we shall be doing, I've already set up a Rust project. But what I'll be doing here is I'll be creating the necessary libraries that we'll need. So what we'll need is we'll create a library, and we'll call it, what should we call it? Let's call it bytecode. Module. Module seems good. And so we'll have that. And there's a few libraries that we'll need. And my keyboard. Alright, but we will need a few dependencies. The big one being bit flags, which we shall bit flags. what else what we might need? I think that's what all we'll need for now. So we have that. Let's see. I mean, let's keep eShell open, but I need to do module rs. Right, so now we need to. So now we need to add our module, which we'll call this high. So high.rs will have our file format, our module format, which will be is a simple bytecode. So let's create a struct and call it file. And I'm gonna do it. We're gonna break this into pieces of a header. Let's call it. I don't think we need that. Because this is going to be very high level. So basically, the parts of a module file that I'm thinking of having is we'll have a header, a section table that describes the format of the file. And then we'll have a string table which holds our string constants, a type table which allows us to identify what type something is, as well as function types and probably closures as well. Effect signatures, function declaration, code, the actual bytecode of each function and effect. Stack map, which defines the structure of the stack at safe points. And a description for our types, which in our case will support what are called tagged unions and tagged unions only. Of a constant pool that has all constants that are not strings, and then debug information. So then eventually when we build in a debugger, we can actually understand what's going on. And for this one, we don't really need the string table or the section table because this will get compiled into a binary. So we probably only need effects. Functions and let's see. I think that looks good. And then we'll put the header up here. And so a header, this will not be all encompassing. Is we'll have a major version, which will be a U16, minor version U16 as well. And then we'll have a magic number, but that magic number will generate once it gets compiled, so it won't store it. And then let's see, what do we need? I've made some notes which I'll not be sharing. So we need to describe so obstruct effects. And basically, effects, which we'll get into more in the nitty-gritty details when we're implementing them. What we need is an effect has a name, which we'll just store as a string. And then we'll have a effect operation, effect operation. And then we need to define a effect operation, which has a name, the string, and then we'll have an arg types effect. Let's call it a type, and return type, which is also a vec of not a vec. Yeah, let's make it a vec of types, because I feel like we could support with our design, we should be able to support multiple return. So now we need to find a type. Now type is going to be an enum. So I'm gonna call, and it's gonna have two variants. It's gonna be let's call it built-in, which will have a built-in type and a user type, which will have a user type. And be like, oh, what are these? Well, we can just do. Hold on. Bit flags. It's been a while since I messed around with bit flags. An example. Struct. Type is a let's do it's an I64, and the reason for that is a built-in type, which we should probably define. Type. Well, basically a built-in type, we'll just negative index it. And then when user type gets dumped in, it'll be positive indices. So to do that, let's call it. Oh wait, I did this backwards. This should be a built-in type. This should be user type. Oh, actually, so why is that complaining? Maybe it is just. That's probably fine. I have to leave the pub there because it's also complaining. Let's see. I'm trying to remember what our types are. Oh, actually, it's simple as we have a int 8, -1, I16 is -2. I32. We will support unsigned and signed integers. It's just that for type's sake, we don't care about that. Only the operations do. So that's why we're free to use something like this. Also, do we need bit flags for that? I don't think we need bit. So I could just do I think I could do this, right? Build type. Is that thing I could do? Post. Oh, okay. I see what I can do. This be an I64, and then I can just delete that. I think. Oh, it won't let me use an I60. Alright, let's just do the bit flags method. It's not pretty. I don't like it. But it seems to work. Actually, this should not be. Looking back at my notes, this should be -2. This should be 3, 4. Actually, no, this should be. I'll explain. Okay. There's a few types that we'll need. The big one, what we'll make, is a type called unit, which are basically void in our case. But. And then the other type one is called never. And these two types are useful for knowledge and understanding things. So, and then we got an F32, an F64, and then I keep on supporting big ints, but I'll just call them int. And let's see, what else do we want? I need a string, which we'll just call an interned string. Make that -10. And a mutable string be -11. And then it's not really, no, think about it. I don't think it, actually. Yeah, I'll just do it. Let's do array byte. And then I can call it const array number. And the reason why we're calling it number and not doing one for each size integer, even though it'd probably be more efficient packing wise, like data wise, only the byte array is the absolute important one. I don't know the last time you really need a short array. But what we will need is an array of, let's call them objects, array object, which this will make sense later on, but basically we need a byte array to be a byte array because there's some things that just need an array pointer of bytes, and this is what we need for it. we need one that stores all the other numeric types. I don't care if we lose some space. If we realistically... No. Should I support the other one? No, I will support the other ones. Why not? It's not too bad. Short... int... long is, I believe, what Java does. So... let's be 16. And so... wait. Nope. We need a float and a double. Okay, so the reason why we need to just make a distinction between these and this is because when we do a step later down the line called verification, which basically ensures that user or compiler doesn't generate bytecode that basically accesses a pointer and the dereferences it, because that would be really sketchy. And we need to make the distinction during the verification step between the different array types. And honestly, these will probably all share the same size. This one will not. And so that's why we have to make the distinction. But another thing we're going to have is we'll have a... what else will we have? I'm going to call it a foreign pointer. It's not really a built-in type, but it's basically just to say, hey, there's something on the stack that is just a pointer, so do not do anything with it. And then there are technically other types that should probably be in there, like a closure. But you can't really represent them as an index, so we'll leave that alone. Maybe rename this from user type to other type. And so an other type, actually this has to be an enum. Actually we could keep the name user type and just add on to closure, which maybe we should actually I think should closures and functions be their own identifiable types. I'm gonna say no, because we want, say, a user in like a programming language passes a function as one instance and then hands off a closure in another, like a conditional. We want them to be the type check and validate to be the same. I think this is safe. I could be wrong, and we'll have to modify it later. But to do that, we need args, effect of type, and return, which I will do this cool thing in Rust where you can escape, and it'll let you just use any keyword, which is kind of neat. And so that should cover built-in types. Then user type. Honestly, I think this should just be a name. And the reason why I think it should just be a name or a string is because we'll eventually just use this to look into the types and then pull the information from that. Because once it gets organized, it should work better. So now we have that. We can now work on effects. effect operation. Now we should add a functions. And so we'll do have a name for the function. And we need the parameters. Be a vec with type, return types. It'll also be a vec of type. So I'll just use return. And then we want to just actually if I can try to use a hash set of strings. Actually, you might even be able to get away with I might be able to get away with that, honestly. Actually, probably get away with that for all of these, now thinking about it. Is we can simply just do and why does that not work? There we go. Oh, that's not good. And that, oh, I see what went wrong. Fix it. Not used to Emacs's, what do you call it? Regex. So that's probably where things went horribly wrong. Alright, so so functions, we need a name for the function, the parameter types, the return types, and then the effects. And in their case, we probably also want to have the byte code. So vec byte of, let's call it spanned bytecode, because I mean, we don't really need to have debug information, but it would be nice to test it. So actually, better idea. Chunk. There'll just be because yeah, this is probably good. And then yeah, that's probably fine. And then now what do we need? We need to do types. Types, and what this will be is simply just be a vec of a type, or not type, let's call them union. And it's quite simple. It has a name, and it'll have I was like, I think like type arguments, but I was like, no, we won't be, for reasons I'll get to later. We will not be monomorphizing anything for reasons. It has to do with Koka. You should research Koka and you learn that yourself. And now we need a variance, which is just a vac of union variant and union variant. It'll just be a simple name, just another static string, and order doesn't matter in this case. Unlike effects, the ordering of effects kind of doesn't matter. Although nothing about it. Actually, maybe we want this to be a vac. Just then it's easier to create from scratch. So this will be a fields should be a vac, and it'll just be a tuple of I don't think we really care about the names. Yeah, we don't really care about the names. So just do type. And then now we need to do the bytecode. I believe. Yeah. So I need for a span bytecode, we just need a let's see, what do I want? Oh yeah, these should probably all nope. So these should all probably be public. Oh wait, what am I doing? I can do this much faster. There we go. Span bytecode, need the line, which could probably be a U32, and pub call, which would be a U32, and that should together take up the same space as a 64, which keeps us aligned. And then we want the actual bytecode. Code, say bytecode. Now we need to find our bytecode. And that we don't want instruct one and enum. And so for this, I have it written down. So what we want to do is do our stack operations. And so our stack operations are quite straightforward. They are push, which takes in a U64, which is just the constant. And then we want a type. Actually, we want probably a subset of built-in type. Let's do operand type. And we can do operand type, which will be either a I8, I16, I32, I64, an F. 32 and F64. Oh yeah, booleans. I think I just remember that. I don't think we care if we manipulate a boolean as an integer. Personally, I don't think it really matters. All right. Is there anything else we want? Yeah, no, that's fine. So basically, this is again for verification. We need to know what the heck we're pushing on the stack. And basically, we only care about the operand type when we're writing it. But once because another step that we'll do in the interpreter is link it. And so we'll erase the operand type after, once we link it. Because we only care about it during the verification step, which we'll get to much later. And so now we have pop, which is quite straightforward. Dupe, which just duplicates the thing on the stack. And then swap, which takes the top two and flips them around. And locals. And we have load. Store local. And then we'll have what are called up values, which you can read about them on Ulua's website. But basically, up values are kind of like if you ever program in C, you can have static variables in a function. Basically turns it into a global that's only seen by that function. Basically, an up value is kind of like that. So we're going to have create up value, which assigns it to slot, which we'll need to store. And then we have a load up value. Put it back. Which now I just remember that these need it as well. Store value. Yeah, so create up value, what it does is an up value is basically a heap allocated slot for a function. And so create up value will create that slot. Load up value will allow us to pull from that slot. And store up value will write to that slot. And load local, store local does the same thing. And because these are U8s, we'll allow up to 255 local variables. No, it's 256 local variables because we allow 0. Yes. And then now we have our arithmetic, which is going to be tedious. So I have I add, you add, and we're going to repeat this pattern. I is going to be, let's make it S. S makes more sense. Signed, unsigned, sub, and we're going to do this many times. Signed. Although, some of these might be redundant if I call my math for a lot of these, but I don't care if they're redundant or not. They give us more information, and more information is always more useful. So let's see, we have our standard arithmetic, and then we have our bitwise operations. We have the AND, or XOR, logical shift right, logical shift left, arithmetic shift left, and then a right shift. If I recall, that's probably all we need. That's because I don't think we have. I don't know. Yeah, I don't think. I think it's fine. Let's see, what else do we need? What else do we need? Comparison. So we need no equality is it doesn't matter because you're just comparing it. Actually, we do want I for integer equality. Actually, I'll think about we need f add. Which takes in a width. Actually, we float width. Actually, int width. This one, nothing about it. All of these will need a width. Mostly because we need they need to be consistent, because honestly C's implicit conversion is sketch. And so I don't trust that, though. Yeah, maybe we do want that. And then this part closer. So there's no f mod. There's an f div. And this appease me. Let's do int width. Int width. Where's my int width? Which would be our I32, actually I8, our I16, our I64, because those are the int widths that we support. And then float width is an F32 and F64. And so, because these don't really care about, I mean, you should probably not do bit operations on a float, but that is something that's technically valid. I'd float equality, and then we need assigned. I actually think NEQ is basically the same as these. And then now is I need complement. Which is technically bitwise negation, but Oh, actually, let's add another section. Let's call it logical, and let's include and. I mean, I don't think we can. All right, let's call it and. Oh. Logical and. Logical or. Logical not. And these basically just care about, is it 0 or not 0? And then we'll do things. I think that's fine. I think it's safer as well. And then we need is assigned less than. Just takes it into width. And then a unsigned less than. And then we want these less than equal to, greater than or equal to, less than or equal to, actually technically that would be that, there. And then let's do conversion, and then we want to truncate, and we want let's make this a little more clear, to int width from an int width. And then for f trunk, basically be kind of the same way. Actually, it's not really, no, we don't want that. That's stupid. We want extend, which is basically the opposite. Technically, you can have an invalid state, but I think it's fine. Because you could have an int width. You could flip the widths and it would be messy, but I think it's fine. And then for a let's call it shrink. And then let's do float width from width. Should I just roll these into one opcode? I'll just convert them into one. Integer. Convert. And so this is will work either shrinking or growing. And int to float. Let's go. Let's do to float width from width, and then go to int. There we go. So now we can convert between float and integers. And I think that's fine. Yeah, I think that's fine. And then we want control flow. Yeah. And what we'll need is, this will come in handy way down the line, but it'll be start block and then a U32. This will be useful way down the line and does not matter for now. So if you don't ever use it, it's probably fine. We want jump, and we want maybe an I32. I think that seems reasonable. And then jump if is also an I32, because these are going to be our unconditional jump and our conditional jump. And these will just be adding on to the program counter. So maybe we want a, do we want to jump at instruction? I think we don't need one. But I think we're fine without one. And then we want a return instruction, which is basically halt the function's execution. We want a call instruction, which in this case we want a static string so we know which function to call. And then we need a call. We need a call tail, which sort of just does the same thing. And then a call closure, which I think we also want to refer to the function we'll be calling. Then what call foreign, which basically is for calling foreign functions, which I'm not quite sure they handled that yet, so I'll just leave it as a static string for now. And then we probably want a call tail closure. And then we want to have a make closure, which this one will also make it like this. And so we want the name of the function we want to use. And then they want the up value count, which will be U8. Then we have stuff for unions. We're going to call it alloc, which yeah, let's give it more information. Let's do name and then variant, and then we want to get field, which This actually will just be a U8, I think, because and then we'll have a set field. And so this is for our tagged unions, and so alloc will create a tagged union off the name and variant, and basically call a function. No, it will allocate the. Actually, do we even? No, we don't even need the variant. Maybe. No, let's keep the variant around because they'll inform the verifier what variant it is and how they'll deal with it, and give us way more information. We shouldn't care about fields because they'll be derived from the size of a union. And then we want to get the tag of a union, and then we also want to do union match, which was take the union and match on the on it, which will require a I might give I32s because basically be building a jump table, and that will be the offset into the jump table for each variant, which now thinking about it, we need to know the variant. So I guess this will be a static string, and so we'll match on the variant. Actually reminds me, I was going to add a match on or it's called switch. It's called let's call it match, which will basically be a vec of a U64 and an I32. So basically our what we're trying to match with, and then the offset into the jump table. And then I want to add one more, which I should call int match, which this is a little more complicated, and essentially it takes in a vec of a static reference to a U64, and that will be for big ints. And then now continue down here. What do we need next? Int. I guess we can have a make big int special, and they get allocated by a special instruction. So let's call it int alloc, or better, alloc int, and that has, since these are arbitrary precision integers, we can do get a lim count. I don't think we really need. I think U8 is sufficient for our purposes. I don't think we need any more limbs, than that amount, but I could be wrong. And arrays. So we want alloc array. I'm in array, and that's just a. Don't we have a constant? So operand type. That's good. And then object array. Just get anything. And what we'll do is we'll take things off the stack for that. Then we want array length. Array store, which we have to be byte specific. Should it be byte specific? Yeah, because then we could just corrupt it. Array store. Let's put operand type. Array get operand type, and that should be sane. Although operand type will be ignored on object arrays. Where's operand type used again? That'd be fine. Technically create a valid state, but I think it's better than nothing. Let's see what else. No, yeah, we need array dupe, which just duplicates the array, and it's a deep copy, so it should be fine. Another one that might be useful is array fill, which just fills it, which should be fine. Oh, I know what we need to add for numbers. Is we need to add a endianness conversion. Call it endian. And then because if we're doing network stuff, we'll most certainly need to support endian stuff. Big, little, and then let's see. Oh, I know it's something we should probably do that. That's too much. We want globals. And we want to do a load global, and this will also be a static str, and a or global must be a static str. And then, now thinking about it, we need to add a new table. globals. We want a globals, I guess is what we're going to call it. Globals, and that just has a pub. Globals, the vec of static str, and then type. And then those will get processed and whatnot later. All right, so array fill strings. Strings will be kind of similar, so we let's call it string, which will be a abstract str, and then we got alloc. Let's call it turned string, mutable string. And basically these will create the requisite object. An intern string is kind of what Java and Python do, in that they are just immutable and you can't change them. And immutable string is more like Rust string type, which it's useful to have both. And when we code the virtual machine, we'll make it so then they can be identified by the functions and they can be handled transparently by either. So, yeah, that's the plan. And then what, string length. I think we get away with not identifying which one. And then we probably want to intern the string if we want to. And then, let's see, do we want turn to mutable, which this will basically give us a mutable string, but from an intern string. I'm just trying to think. Oh, you probably want a byte conversion. String to bytes. That will just convert either of the string types into a byte array. And string comparison might be better handled by just function calls, so I will probably just not add the instructions for comparison because I don't think we need them. And then this should have been up here. I think this is a subset of control flow, but we need effects. So we need to push handler, which we need a static string for identifying the effect, and pop handler for the same reason. I guess this could also take another. This one needs a little more information. Is we need a name. Actually, it's probably effect name. Stir, and then we need to do handler, hook in the handler function that gets called. And I'll also put in a static string. And then we need to add perform, which will basically perform an effect handler. So I need, what do I call it? Did I put this in the wrong spot? Yeah, I put that in the wrong spot. So we need these. So we can identify which one we're doing. And then we need what's going to be called unwind. And unwind is special. Basically, perform is a resumption, or rather, it will resume. So what happens is when we do a perform, what happens is we basically go down the stack, although we'll make, in layman's terms, we go down the stack, find the handler, execute its code, resume back at where we were with whatever values on the stack. Unwind, on the other hand, we'll just go through the entire stack, unwinding everything. Basically, we're not going to be resuming. So, and then we need a resume, which basically is once you do a perform, we execute a resume, and resume basically takes us back up the stack. Now, it's kind of slow to explore the stack to find that right handler, so we'll be looking it up with a constant table once we get into the linking step. But we're not there yet. And then I guess this is kind of... I guess we can do this now. Async. We will support we'll have to do some logic for async within our virtual machine, but for now we'll have spawn, await, and yield, which basically are the primitives that we need to get async working. Because actually I should probably explain more. Is the async model I want to support is more like something provided by Rust Tokyo, which allows us to have multiple threads so that whenever we spawn a task, you can start being made on it in like a thread pool. Unlike JavaScript, where everything's single threaded and we only make progress when we want to await something, which is not optimal. So, and then we have reference counting operations of inc, dec. We have what's called try reuse, which basically, if the reference count of something is 1, it will not immediately deallocate the memory. It'll keep it around until we do a reuse, which will basically pull from the reuse. And then is unique is to identify if the object that we're looking at, is it a unique type? And then is shared is to identify whether or not the reference count indicates that it is a what do you call it? A atomically reference counted type. And then we're going to do a make local, which basically will convert any atomically reference counted type into a reference counted type. And then a make shared will essentially do the opposite. And we have a duplicate, which this will do a deep copy of any union type, essentially. Which I don't want that. And then foreign. This is for like foreign types. Is we basically every type will have a deconstructor and constructor. So we set destructor and set clone function, because also a type can be cloned. And so for our heap allocated types, it'll basically do nothing. And then I think that's all that we need. Actually, so that we need to do is we need to load a foreign function, and I think I'll just put a static string there first. And so I think that looks good. Oh yeah, we probably need to stack. Do we need the stack map? Probably want the stack map. Section. Well, let's see. I think I'll call it quits for today. I think we did a lot. I gave you an introduction to my project. I have started setting up the types. And this is bothering me. Can I fix this? I did spell it wrong. Let's fix this. And so I think we set up the bytecode. I guess next time I'll probably go and what I'll do, I'll probably build out the lower level types. I might do that on camera or off camera. I'm not quite sure. But I thought I would do more, but I'm getting kind of tired. But I think that'll be it. So see you guys next time.